Okay, everyone, in the last video we learned what a logarithm is and come to find out that a logarithm is just the inverse of an exponential function. And we learned how to graph those logarithms and also transform those logarithms back into an exponential form. Today we're going to move on and learn some more properties about logarithms. So our objective today, we're going to be able to simplify expressions using the product, the quotient, and the power rule of logarithms. We're also going to solve logarithm equations applying the product, quotient, and power rules. And let's start with some of these properties. So the first property that we're going to talk about is the product rule. Now we've got some jargon here. For all positive numbers a, b, and x can't be the number 1. Then it says that log base x of a times b is going to be the same thing as log base x of a plus log base x of b. So product, when we multiply numbers, we can pull that log apart and have two separate logs of the numbers with a sum. So here's a concrete example. Say I have log base 2 of 30. 30 could be rewritten as a multiplication of two numbers. So if we factor it apart, we have 5 times 6, since 5 times 6 is 30. Using this property, the product property, I can pull this apart and have two separate logs for the 5 and the 6. So log base 2 of 30 or log base 2 of 5 times 6 is the same thing as saying log base 2 of 5 plus the log base 2 of 6. So here's how you'll do this on homework. In your directions, it's going to say use a particular log as a decimal, and then it wants you to approximate a value. So here we're going to assume that log base 4 is going to be the decimal 0.7925. We're going to approximate its value of log base 4 of 192. So in our approximation part, log base 4 of 3, we're going to try to see if 3 can go into 192. And if I use the calculator and take 192 divided by 3, you're going to see that 192 is the same thing as saying 3 times 64. Now I can apply the product property, and pull those apart and have two separate logs. So I have log base 4 of 3 plus log base 4 of 64. Now going back up into directions, we're supposed to go ahead and assume that log base 4 of 3 is already 0.7925, so I can replace that part. That's a substitution. Now, however, log base 4 of 64, the calculator doesn't just immediately do that for you. You're going to have to use this thing called the change in base formula. Log base b of a, so if you got a log with a particular base, you can use the calculator to do log of a divided by log of b. So that being said, you'll have to type it in this way into your calculator. Now, if you have a calculator of a TI, right here I have a log button. So if I type in log of 64, close my parentheses and divide it by log of 4 and hit enter, it's going to come out to give you 3. So that being said, I get to replace that log 64 over log of 4 with a 3. Add the two numbers together, and we get 3.7925 approximately. So that's what log base 4 of 192 is approximately when it's rounded. Now the quotient property. So now say you have a log that looks like a fraction on the inside. We can pull that log apart and have subtraction with it. So if I have log base x of a over b, it's the same thing as me saying log base x of a minus log base x of b. So another example, say I have log base 2 of 5 over 6. I can pull those apart and have a subtraction between the two logs. So I have log base 2 of 5, the top will always go first, the bottom goes second with a subtraction. So log base 2 of 5 minus log base 2 of 6. Let's try another example. This time in my directions I have two different logs that I'm supposed to assume have a decimal value. So here we got log base 4 of 3, 0.7925, the same as our previous example. Now we have log base 4 of 5 is approximately 1.1610 to approximate the value of log base 4 of 5 over 3. So I start with the problem. Since I have a quotient, I'm going to go ahead and break this apart into a subtraction problem. So the top goes first, log base 4 of 5 minus log base 4 of 3. Now you'll notice that both of those logs are in my direction, so I can substitute their approximate decimal values into the problem. So log base 4 of 5, the direction says it's 1.1610 minus whatever log base 4 of 3 is, so 0.7925. I subtract the two decimals. Approximately, this is 0.3685. So there's the quotient property. The last property we have is the power property. For any real number p, so we're talking about the exponent, and the positive number m and b, where b is not equal to 1, so our base can't be a 1, if I have an exponent that I'm trying to take a log of, I can take the exponent from the inside of the log and pull it out front to the outside of the log. So an example, say I have log base 2 of 6 to the 5th power. You see that I have 5 highlighted in red. That's because that 5, by rule, can get put out front and they are considered the same thing. So let's apply this property. So log base 2 of 5, we're going to approximate that as 2.3218 or 19. Approximate the value of log base 2 of 25. Now you look at my log base 2 of 25, you might think, well, where's the exponent at? But isn't 25 a perfect square? Can we think of another way to rewrite 25? And you should be thinking that 25 is the same thing as saying 5 to the 2nd power, or 5 times 5. Now you see that I have an exponent. So by using the property, or the power property, I can take the 2 out front of the log, and I've got 2 times the log of log base 2 of 5. I'll look back into my directions. We have log base 2 of 5 is already going to be 2.3219. So I do that, replacing 2 times 2.3219. That'll give us a value of 4.6438. So that's using the power property. Now there are some ways that I could go in and show you how these properties were derived, but I figured I would save some time by not going through them and go ahead and let you just assume that they are true. So we want to be able to use those properties now to solve some logarithmic equations. So our goal here, use the property of logs to either put the equations back together to solve them, or we can pull them apart. Now, I've shown you the properties in this form where I said we're log and we pull them apart with a sum. But we can flip that around and say, well, what if it's already pulled apart? We can go ahead and just push it back together. They're interchangeable. You can go from left to right or right to left. The same is true with the quotient property. So this is the original form that I showed you. But if I flip it around, I can take it already broken apart and put it back together as a quotient. And lastly, the same thing with the power property. If we took the exponent and pulled it back out front, we can take the number that's out front and put it back into the log. And I'm going to show you how to do that with some examples. So first off, I see the problem. I might say, well, how do I get started? Well, the first thing I notice is that there's a plus sign here. That plus sign tells me that the product property was in use. So instead of pulling the problem apart, I'm going to push the problem back together. So I had 2 log base 6s. I push it back together. Now I've got x times x minus 9. That's still equal to 2. Now going all the way back to Algebra 1, anytime we've had grouping symbols, we would distribute through. So now I have log base 6 of x squared minus 9x. Now, well, where do I go from here? Well, kind of a dead giveaway on this is there's 2 ways to solve this. You can either convert it back to an exponential form, or sometimes if you have logs on both sides, we can go ahead and drop the logs. Here I only have 1 log, so to me that says that's a dead giveaway to convert it back to an exponential form. So converting it back, remember, drop the base. What it's equal to is the new exponent, and what we're taking the log of is what's going to go on the other side of the equal sign. So here's what it is, convert it back into an exponential form. 6 squared equals x squared minus 9x. Do some simplification. 6 squared is 36. And we have a quadratic here, so whenever we solve quadratics, we've always got to get it equal to 0. So I'm going to subtract 36 back over to the other side. Now you might be thinking, well, how do I solve this? Remember our AC method of factoring? I'm going to go ahead and do that. The number in front of x squared is a 1, so 1 times negative 36. I'm looking for 2 numbers that multiply to give me negative 36. They're going to add to give me the middle number of negative 9. Go through, think of those numbers, and think. The 2 numbers that you should come up with are negative 12 and positive 3. I take those 2 numbers, replace the minus 9x in the middle with the negative 12x plus 3x, and I go and do factor by grouping. So I'm going to group both the first 2 terms and the second 2 terms and see what we have in common. With the x squared and the minus 12x, they have an x in common. With the 3x and the minus 36, they have a positive 3 in common. So this in factored form is x plus 3 and x minus 12. And of course, when we solve quadratics, we're always supposed to set those equal to 0. So if I had x plus 3 equal to 0, solve it, you get x equals negative 3. X minus 12 equal to 0, and you solve it, you get x equals positive 12. But here's the problem. Both of these are not always going to be a solution. Just like when we had our radicals, where we had an extraneous solution, there was a possibility that we might have extraneous solutions when it comes to the logs. So I'm going to take those numbers, go back to my calculator, and I'm going to plug them in and see what happens. Go back to my original problem, and I'm going to plug in, I'm going to start with negative 3. And again, I can't type in a log base 6, so I'm going to use my change in base formula. This will be log of negative 3 divided by log of my base, which is 6. And I'm going to go ahead and hit equals there. What you'll see is that it says domain error. The thing is, we can't take logs of negative numbers. So therefore, when we get a domain error, that tells us that we've got an extraneous solution. So negative 3 is going to be extraneous. Now let's go over to 12 and make sure that works also. Let's see. Log of 12 divided by log of my base of 6. That's going to give us this decimal. I'm going to leave that there. I'm going to go ahead and hit plus log, and I plug 12 into the parentheses. 12 minus 9 will give us 3 divided by, again, log of my base, which here is a 6. I hit equals. And see, I get 2. 2 would be on the left side. The equation is equal to 2, so 2 equals 2. Therefore, 12 has to be a solution. So 12 is my solution. I'm going to circle it, and then down here I'll say negative 3 is an extraneous solution because we weren't able to take the log of a negative number. That's using the product property. Now, you can use some of the more than one property in a particular problem. I go through and I scan the problem. The first thing I notice, there's a 2 out front, so that tells me that I can throw the 2 back into the log for the exponent. So I'll have log base 7 of x squared. I look to the right side of the equal sign, there's a plus sign. So that's a giveaway that we've got the product property. I squeeze the logs back together. I have log base 7 of 27 times 3. I simplify the 27 times 3 and I get 81. Now here, this is different than what I had in the last problem, because in the last problem I only had one log on one side of the equation. Here I've got a log on the left side and I have a log on the right side. So this is very similar to whenever we were solving exponential equations, that if our bases were the same, we could disregard the bases and worry about the exponents. Well, here we have log with the same base. So I'm going to disregard the logs, and I'm just going to focus on when is x squared going to equal 81. Solving that equation, we would take the square root to both sides, and when we take square roots, we get an even root, so we have to worry about the plus or minus. So right now, x could be equal to plus or minus 9. But again, we have to be careful, check for extraneous solutions. So then I go in, back to the calculator, go back to my original problem on the left side, 2 times my log. Again, we have to use the change in base formula, and we're going to plug in positive 9 divided by log of my base. Right now, the left side of the equation is 2.2583 and so on. Check the right side. Again, we'll have to use the change in base formula. So log of 27 divided by log of 7 plus log of 3 divided by log of 7. And I get the exact same decimal, so I know that positive 9 is a solution. I'm going to go back in and I'm going to check with negative 9. Now what's nice with the calculators is that you can go back in and arrow up and change whatever you need to change. So here, the only thing that we need to change is, instead of putting in a positive 9, we're going to make that a negative 9. and I hit equals, because I plugged in the negative number. Again, we weren't able to take logs of negative numbers, so therefore we had a domain error, which makes -9 an extraneous solution. So my only solution here is +9. The last example that I'm going to go over is with a quotient rule. So if I look at the problem here, I see a minus sign, so that tells me that I need to use the quotient rule to put this problem back together. Whatever's on the left side, though, goes on top of the fraction. Whatever's on the right side of the subtraction sign goes on the bottom. Now I have the quotient rule set up. It's still equal to log base 4 of 9. Similar to what we had in the last example, I have a log on the left side and I have a log on the right side, so I can disregard the logs. I have 48 over n equals 6, and we solved that like we did in Algebra 1. Multiply both sides by the n, you get 48 equals 6n. Divide by 6, so n has to equal 8. Now I go back to the calculator to make sure that this is a solution. Start with the log base 4 of 48 using the change in base formula. So log of 48 divided by log of 4 minus, we're plugging in a +8 for n, so that's going to be log 8 divided by log 4. We get 1.29 and so on. And as long as this works out where I put log base 4 of 6 in the change in base formula and I get the same number, we'll be good with the solution. Now you see we get the same decimal, so therefore n equal to 8, that is my solution. Okay, so let's recap. So we've learned to use the product, the quotient, and the power properties to break apart problems and evaluate the logs. But we were also able to use these product, quotient, and power properties to put the logs back together to solve for the variable and equations. And one thing that you do need to remember when you do solve the equations, that we always got to check for extraneous solutions and identify them. So there you have it. That's the properties of logarithms.